Part 3, this is for questions 21 to 30. Question 21, which statement is correct? The first option, hydrogen bromide reduces concentrated sulfuric acid to form sulfur dioxide. This one is true. Let's look at hydrogen bromide and then plus sulfuric acid. Then we get bromine plus sulfur dioxide, then plus water. This one actually comes from sulfuric acid reacting with, let's say, sodium bromide, then to give you this sodium hydrogen sulfide. Then remember, as you go down the group, these elements of group 7, they become beta reducing agents. Okay, the oxidizing power reduces. So now sulfuric acid becomes a beta oxidizing agent, and when you have a reducing agent and an oxidizing agent, the reaction is very fast. Okay, then what we have here, let us look at the oxidation state of sulfur here. Of course, for hydrogen it is 1, then sulfur is the one that I'm looking for, and then for oxygen here the oxidation state is a -2, but there are 4 of them, then is equal to 0. This is -8 plus 1, that will be negative what? No, actually here we are having a 2 because there are 2 hydrogens. Okay, so this will be -6, and then when the 6 crosses, it becomes a +6. Then here, of course, the one for bromine is -1, the one for hydrogen is +1. Then now here we are having a 0, you see. So if here I'm having a +6, then here n plus 2, then times -2 is equal to 0, and then n becomes a +4. So here we have a +4. Now from 6 to 4, this is reduction. So that means here sulfur has been reduced. So when they say hydrogen bromide reduces sulfuric acid, so we are looking at the oxidation state of sulfur here. It has changed, it has reduced. And then this one here has been oxidized, okay, from -1 now to 0. So this is oxidation. So a reducing agent is oxidized in return, and then an oxidizing agent is reduced. So sulfur here is acting as an oxidizing agent. You see that? So A is correct. They are talking about the sulfur dioxide gas, which is here. Then for iodine, if we have, let's say, hydrogen iodide and it is reacting with sulfuric acid, you also get iodine. Then you can get sulfur dioxide, and then you can get water. Another one is also iodine, then there is also water. Again iodine, and then there is also water. But here we can get sulfur, and then the other one is hydrogen sulfide. So these are the possible equations that we can have when hydrogen iodide reacts with concentrated sulfuric acid. I've not balanced them, okay, but that is that. Then let's continue. Let's look at option B, by the way. Hydrogen bromide decomposes at a higher temperature than hydrogen chloride. No, this is wrong, because bond energies for this group 7 hydrogen halides, actually we have hydrogen halides. This one is stronger because chlorine is more electronegative. Okay, group 7 elements are more electronegative, yes, so they tend to pull the bonding electrons towards themselves. So these molecules here are polar, but again, as you go down the group, these ones become larger and larger. So because this one is so large, then the attraction between the bonding electrons and the nuclei is weaker, so they will form long bonds which are weaker. So the bond energy below, as you go down the group for these hydrogen halides, decreases, you see. So that means it is easier to break this one down compared to hydrogen chloride. So that's why this one is off. When hydrogen bromide gas is shaken with aqueous silver nitrate, a yellow precipitate is formed. No, it is supposed to be a cream precipitate of silver bromide. The yellow one they are talking about is for silver iodide. You see that? So even this one is off. When hydrogen bromide gas is bubbled through aqueous iodine, the solution becomes colorless. Here, since bromine is more reactive than iodine, then it is going to displace the iodine from the solution. Okay, the iodide ions are going to be oxidized to iodine, and the color is not going to be in this one colorless. It is going to turn a bit brown or darker. Okay, so that is why this one is also off. Question 22. Iodine monochloride is made when chlorine and iodine react together. This is the equation here, and they are saying iodine monochloride reacts with water. So this is the equation, and then they are saying which row is correct oxidation number of iodine in iodine monochloride. So we look for the oxidation state here. Now here, these two are electronegative, but chlorine is much more electronegative. So because chlorine is much more electronegative, it is the one that is going to pull the electrons towards itself much more. So the dipole moment is going to go towards the chlorine. So chlorine will attain that negative, and then iodine will have the positive. So here we have positive 1 for iodine, and then negative 1 for chlorine. So that means these two, we shall put them off. We have to be here, okay? Then they are saying the reaction occurring when iodine monochloride reacts with water. What do we see? Iodine atoms are oxidized, so we have to look for oxidation and then reduction. In other words, let us look at the oxidation number of iodine here and also here. Of course, since this one is an element, the oxidation state of any element is 0. Then how about here? We have N. For hydrogen, it is 1, so 1 plus. The one for iodine, we don't know. And then for oxygen, there are 3, then times the negative 2, then it's equal to 0. So this one will be negative 6 plus 1, that is negative 5. Then when the negative 5 crosses the equal sign, it becomes a positive. So N is equal to plus 1, 5. So here we have a plus 5. Now, the iodide is plus 5. I mean from plus 1 to plus 5. So this is oxidation, not so? And then from here to here, that is reduction. Okay, that is actually what we call disproportionation reaction. We see one species is both oxidized and also reduced at the same time. Okay, now here the iodine atoms are oxidized to iodine, but to iodine we are seeing what? Reduction. So that means this one is off. Already I had the ticks here, but since this one is off, that means our answer has to be B, which says that the iodine atoms are oxidized. Iodine atoms are oxidized to form this hydrogen iodate. So, and this is actually oxidation to hydrogen iodate. You see? So there is a tick there. That is why our answer is B. Question 23. Ammonium chloride reacts with sodium hydroxide in an aqueous solution. Which statement is correct? So whenever you warm any salt of ammonia with a strong alkali, you will always get ammonia as a gas given off. So we have ammonium chloride plus sodium hydroxide. So first put off the ammonia with its strong pungent smell, then plus what else shall we have? Sodium chloride and then water. Okay, balancing this one, because this one is like an acid-base reaction, because this one here loses the hydrogen ion to this. You see? So it donates a proton to this. It's an acid-base reaction. Is it balanced? Yes, I think. This is 3, then plus 2, that is 5. This is 4 plus 1, 5. Oxygen 1, chlorine 1, sodium 1, sodium 1. So that is what we get there. Now let's go to the options. The reaction gives rise to 2 different polar products. molecules. Now they are talking about molecules. Sodium chloride is not a molecule. Okay, molecules are for covalently bonded compounds. Okay, so atoms which are covalently bonded, they give rise to molecules. This water is polar. Why is water polar? Because oxygen is more electronegative, so it tends to pull the bonding electrons towards itself. Okay, so it attains a partial negative charge, and this one a partial positive charge, the hydrogens. Okay, so this one is polar. Even ammonia here, ammonia is also electronegative. This one even forms, just like water, it forms hydrogen bonds. Okay, so something that is not polar cannot be in position to form the hydrogen bonds. So we see ammonia here, the lone pair of electrons here, it can be donated. You know, we have three elements that form hydrogen bonding: nitrogen, oxygen, and fluorine. Okay, so long as they have hydrogens which are connected to them, then they can be in position to form the hydrogen bonds. You see, so what actually determines the number of hydrogen bonds formed is one, the number of lone pairs and the hydrogens connected to them. You can see here in water, oxygen has two lone pairs. You see that? So, and the two hydrogens connected to it. That means it can form the two hydrogen bonds. But here in ammonia, you are seeing three hydrogens, but this one, you would expect it to form three hydrogen bonds, but it will form one hydrogen bond because it has one lone pair. You see that? Okay. So these two are polar, this and this one here. So we shall therefore get A. So that is actually why this ammonia here can dissolve in water. Water is polar, so this one also has to be polar. You get that? Okay. Then the bond angle in the nitrogen containing species. Now I'm showing why these ones are wrong. The bond angle in the nitrogen containing species remains unchanged. For this one here, I will take the ammonium ion. So the ammonium ion here, we are having what we call the coordinate bond. Okay, where the lone pair on this ammonia is donated to a hydrogen ion or the proton, and then you get that. You see, so when you look at this one here, this structure here is tetrahedral, that is 109.5. This is going to be the bond angle. But then in ammonia, using valence shell electron pair repulsion theory, because of this lone pair bond pair repulsion is stronger than bond pair repulsion. So the angle here is going to be smaller than this because of the stronger repulsion that is coming from the lone pair here. You see? So below this one here, we can choose 107. So there is change in the angle. You are moving from a tetrahedral structure to a trigonal pyramidal. You see that? So when they say the bond angle in the nitrogen containing species remain unchanged, that is wrong. And then this one here, the ammonium ion acts as a base. It is wrong. The ammonium ion acts as an acid because it donates a proton to this one here. You get it? And then here it has the three hydrogens, so it donates a proton. So what donates a proton is actually an acid. You see that? And then the oxidation state of nitrogen increases in the reaction. The oxidation state of nitrogen, here it's a -3. And then here it is also -3. It remains, it doesn't change. Let's prove. This one is N, then plus 4 times 1, then plus -1 for chlorine. Then we equate this one to 0. And then 4 minus 1, this one will give you -3. And then when it crosses, this one will give you +3. When it crosses, it's a -3. So you see that the oxidation state doesn't change. You see? So that's why this one is wrong. What is produced when 60 grams of nitrogen monoxide reacts with an excess of carbon monoxide in the catalytic converter? So the first thing we need to know is the equation. So when carbon monoxide reacts with nitrogen monoxide in the catalytic converter, we form carbon dioxide and then nitrogen as a gas. to balance this one here, nitrogen here is 2, so I can put a 2 here. And then if I put a 2 here, carbon becomes 2, and then also here it will become a 2. Then oxygen is 4, then 2 plus the 2. That is that. Now, this is a reaction that helps to minimize the production of these oxides of nitrogen, because if oxides of nitrogen get into the air, then we are going to have that nitrogen dioxide reacting with sulfur dioxide. Remember, this is an impurity in fossil fuels. You get it? Sulfur is an impurity in fossil fuels. So when they burn them, then we get the sulfur dioxide. And then when these two react, we get sulfur trioxide, then plus the nitrogen monoxide. You see this? We call it the catalytic oxidation of sulfur dioxide. Now, from here, we are going to have this nitrogen monoxide, because in the air there is ready supply of oxygen, so plus an oxygen here, then you get nitrogen dioxide. Why we call it a catalytic oxidation? Here it appears to have been consumed to produce this, but again, when this one reacts with oxygen again, we see this one coming back. Now the process continues, but this sulfur trioxide formed here, it is going to react with the water, and then it forms the sulfuric acid. This one is going to give you the acid rain. You see that? So this reaction in the catalytic converter helps to curb this problem of acid rain, because here nitrogen that is produced here is inert, first of all, and it is not dangerous. Okay, all right, so that is that. Now let's go back to the question here. They are talking about the grams of carbon and then 92 grams of nitrogen dioxide. So first of all, we don't get nitrogen dioxide, we get nitrogen. You see? So this one will be off. Even this one will be off. So we are seeing carbon dioxide and nitrogen. Okay? So that means our answer is either here or here. Now let's check. From here, since they are talking about masses, what is the AR for carbon is 12. Then the one for oxygen is 16. Then here the AR for nitrogen is 28. No, it is 14. Then plus that of oxygen is 16. Then here we have 12. Then plus 2 times 16. That is 32 plus 12. That is 44. And then here 2 times the 14. So meaning this one is what? It is 28. So 28 times 2. But now let me center on nitrogen monoxide. So this is 30 times 2. This will be 60 grams. So in this reaction, we are seeing 60 grams of nitrogen monoxide. And then they are talking about with an excess of carbon monoxide in a catalytic converter. Then we are seeing carbon dioxide and nitrogen. Okay. Now let us look at carbon dioxide. This is 44 times 2. That will be 88 grams. And then this one here will be 28 grams. So when they say when 60 grams of nitrogen monoxide, already this is 60, reacts with an excess of carbon monoxide, we are seeing 88 grams of carbon dioxide and 28 grams of nitrogen. That means our answer is what? C. Question 25. Which alkane shows geometric isomerism? Now in geometric, we are seeing cis and trans. That means the two carbons in the double bond here, okay, must be having two different groups attached to them. One can have two different groups, but then another one fails. That means there won't be geometric isomerism. You see that? So let's look at the first one here. There are two hydrogens here, so this one is off. Then when you look at this one here, we are having a carbon double bond, this one here. I can put the hydrogen here, then the CH3. These two groups are different. Let's check this carbon here. There is a hydrogen, and then there is this ethyl group. So if there is an ethyl group here, this group is also different from this. Now, this one is the so-called cis, okay? Because these two are on the same side, okay? Then this one can come down, and then this one goes up, then we can have the trans. So this one can actually have the geometric isomerism. But when you look at this one here, two hydrogens already, so that one is off. When you look at this one here, we have two methyl groups, this one and this one here on the same carbon. So that's why also this one is off. Question 26. What is the correct name of the major product of the reaction of hydrogen bromide with 3-ethyl hex 3-ene? So let's first write this one here. We have 1, 2, 3, 4, 5, 6 because it is hex, okay? Then the double bond is going to be on the third one, 1, 2, 3. So the double bond will be here. And then on the third one, that is where we are seeing the ethyl group. So CH2, CH3. Then from there, that means here we have a CH3, then here is CH2, and then here is CH, then CH2, CH3. Then when we bring in hydrogen bromide, when this one draws closer to this molecule here, remember, bromine is more electronegative compared to hydrogen, so it has a partial negative charge as it tends to pull the bonding electrons towards itself. Then hydrogen is going to have a partial positive charge. Now, because of the electron density in the pi system here, then this one will donate these electrons to, we call it an attack. Then this one will now break off. So what are we then going to have? CH3, CH2, C, then CH2, CH3. Then here, the hydrogen can go onto this one or onto this one here. But I already said the rich get richer. Look at the carbon with many hydrogens in that double bond, okay? It is the one you first give the hydrogen. So we shall have a CH2 here. Then there is a CH2 and then a CH3. Now this one becomes positively charged. This is a carbocation. It is a tertiary carbocation. So this tertiary carbocation will be stabilized, you see, by these three alkyl groups. There is a greater positive inductive effect here, okay, than when we have the hydrogen, here, okay, then the plus here. That means we have one alkyl group here, okay, and then this one here. That means that is a secondary carbocation. So the positive inductive effect here is not strong compared to the tertiary, okay, compared to the one that comes from the tertiary carbocation. So that is why this one becomes the minor product, and the one with the carbocation here, this one here, this one is much more stronger, so it will give us the major product because of these three alkyl groups that produce a stronger inductive effect. That is using what we call Markovnikov's rule, okay? Then from here, the bromine now can come in, and then it donates its lone pair of electrons to that. Then what else do you come up with? You have CH3, CH2, then C, then there is this Br, then there's a CH2, CH2, CH3, and then the ethyl group here. So they are saying, what do we get? We need to get this name here. So bromine is on the third one here. So 3-bromo. Then there is also 3-ethyl. Okay. Then hexane. So 3-bromo, 3-ethyl, hexane. That is our answer A. Question 27. The alkane 2-methyl-butane. Is this 2-methyl-butane? Let's say this is CH3, CH2, then CH. So there is a CH3 here, and then there is another one here. So this carbon is connected to two CH3s. So this one is on the second carbon. Yes, it is 2-methyl-butane. So the alkane 2-methyl-butane undergoes free radical substitution with chlorine. No carbon-to-carbon bonds are broken in this reaction. Remember, alkanes are unreactive because of the circulation of the carbons. Okay. Now, to make them react, it is done under UV light, okay, where we have 3 steps. The first one is initiation, where the chlorine is homolytically broken down by the UV light to produce 2 radicals. Now these radicals are very reactive, then they can attack this one here, okay. So we get a molecule now reacting with a radical, then to produce another molecule, and then more radicals, that is propagation. And then when 2 radicals come together, that is the termination step, you see. So in that free radical substitution, it goes on, and we can find all of these hydrogens replaced, you see that. So it forms a mixture of products. Now let's go to this one here. They are saying how many isomeric products, including positional and optical isomers of molecular formula, this one here can be formed. Now let us begin by replacing a hydrogen here with a chlorine. So you will have CH3, CH2, then CH, then there is CH2Cl, and then there will be here a CH3, okay. Now when you look at this one here, and they said including positional and optical. So for optical isomerism, then I'm going to look at a carbon with, a chiral center. So with 4 different groups connected to it. This is ethyl, this is methyl, then there is an alkyl group together here with the chlorine, and then there is a hydrogen. So this means that this carbon here is a chiral center. So it will give us 2 enantiomers, okay? Those optically active molecules. So those are 2. Then I can also put the chlorine here, okay. If I put the chlorine on this one here, it is the same thing as putting it here, okay, because this one can still be my parent chain. 1, 2, 3, 4. Then this one, the CH3 here, can still be the substituent. So you see that. So putting the chlorine here or here, it's the same thing. Then I can shift and put the chlorine here on the second one here. So I can have CH3, then CH2, then C, and then that hydrogen is replaced by the chlorine. Then there is a CH3 here, and then there is a CH3 here. First of all, these 2 groups are the same, so this one is not a chiral center. Are we there? Now this is 2 chloro, 2 methyl, so this one will give us 1. Then let us put also chlorine here. We can have, this one is 1, you have CH3, then CH, chlorine, then there is CH, and then CH3, then CH3, okay, just like we had this one here. Just put the chlorine here, and still this carbon here is connected to 4 different groups. There is this one, there is this one here. No. This one here is not a chiral center, okay, because this is CH3 and this is CH3. That means this one gives us 1, okay. Then there is a possibility of also having what? There's a possibility of having a chlorine here, not so? A chlorine here. Now let's check this one out. We shall have CH2, then with the Cl here, then CH2, CH, then CH3, and there's also CH3 here. You see? Now, do we have a chiral center here? No. So even this one is giving us what? 1. So they say the positional. That means you look at chlorine wherever it is going. You see? Pardon me here, by the way. When you look at this one here, this one is a chiral center because it is connected to this CH3. There is the chlorine, there is a hydrogen, and this other group. Yes, so this one is not a chiral center, but this one is a chiral center. So that means this one is giving us 2, okay? It will give us 2 optical isomers. So now we can have 2 then 1, those are 3, 4, 5, then 6. So that means our answer is C. Question 28. What is involved in the mechanism of the reaction between aqueous sodium hydroxide and 1-bromobutane? Aqueous sodium hydroxide, we have halogenoalkanes. Now, if this one is aqueous sodium hydroxide reacting with a halogenoalkane, we get an alcohol. But if the sodium hydroxide is put in ethanol and then it reacts with these halogenoalkanes, we get an alkene. That is an elimination reaction. This one is a substitution reaction. So let us look at bromobutane. This is CH3, CH2, CH2, then C. I can put the hydrogen here and then this one here. Then I project this one very well because this bromine is more electronegative compared to carbon. It attains a partial negative charge, and then this one a partial positive charge because it seems to be losing electrons to the bromine, right? Then we are going to get this OH. So this one happens under SN2 because there is only one alkyl group that is donating electrons to this carbon here. So it's not stabilizing this carbon here enough, okay, to undergo SN1, that this one just gets off. But that one happens in tertiary halogenoalkanes. So this one therefore donates the electrons to the carbon with a partial positive charge, and then this one breaks off. Then we are going to have CH3, CH2, CH2, then there is CH2, and then OH, then plus the bromine here, which is given off, the bromide ion. So they are saying attack by a nucleophile. A nucleophile, nucleo, things that are in the nucleus, we have protons and neutrons. Phile means love. So what loves what is in the nucleus? Because protons are positively charged, then must be negatively charged, or must be in position to donate the lone pairs. So a nucleophile is that species that donates the lone pairs of electrons, you see? So this one is a nucleophile here. So an attack by a nucleophile on a carbon atom with a partial positive charge, and you can see this one is a partial positive charge. So the answer is A. You see? I don't need to look at the rest. That is that. Question 29. But2-in reacts with cold dilute acidified potassium permanganate to give product X. But2-in reacts with an excess of hot concentrated acidified potassium permanganate to give product Y. Which statement about X and Y is correct? Now let's see. Here, with cold dilute acidified potassium permanganate, alkenes produce what we call diols. So which diol are we going to have? CH3, then CH, remember there's CH here, and then CH what? 3. So with this double bond there, it goes away, and then we have an OH here, and then an OH here. This is our X. Then but2-in reacts with excess hot concentrated acidified potassium permanganate. Now with this one here, we get the double bond. It is completely broken down. Okay. Then when it is broken down, oxidation takes place here and here. Now you are going to get an aldehyde from this end, and also here an aldehyde. But again, they said excess. Even if this word excess isn't there, the fact that this one is hot and concentrated, then further oxidation takes place, and then you get a carboxylic acid. So from here, we shall get a carboxylic acid, which is CH3COOH. So this is our Y. Now, they are saying only one of X and Y reacts with the 2,4-dinitrophenylhydrazine. 2,4-dinitrophenylhydrazine is used to give to test for the presence of carbonyl compounds. So if it is an aldehyde or a ketone, then they will give that orange precipitate. But we are not going to see this one happening because the aldehyde that is formed here is again oxidized to a carboxylic acid. So a carboxylic acid does not give a positive test with 2,4-dinitrophenylhydrazine. You see that? Then, so that means this one is wrong. Then we go to B. X and Y both react with sodium hydroxide. No, it is carboxylic acid which reacts with sodium hydroxide. An alcohol, this one here does not react with sodium hydroxide. Well, when you go to A level, you will study about phenol. Phenol, this one is also an alcohol. This OH is on the benzene ring, but because of the delocalization of the electrons on the oxygen into this ring here, this one can be in position to lose this hydrogen. So this one is acidic, but these ones are not acidic. Okay, but that explanation will come in A level. You see that? So therefore, we are not having a reaction there. So sodium hydroxide can only react with Y, not X. So this one is off. X and Y both react with sodium metal. Yes, these ones, the alcohols, react with sodium metal to produce hydrogen gas and sodium alkoxides. In other words, I will have a sodium here and then a sodium here after the reaction. So that is what we call sodium alkoxide. And then this one here, this is an acid, it reacts with a metal. So it will also derive hydrogen gas from here. And then you get sodium ethanoate. You see that? So this one is correct. But then D, Y reacts with lithium aluminium tetrachloride to give X. Y is a carboxylic acid. This one is a reducing agent. So this one, the lithium aluminium tetrahydride will reduce this carboxylic acid to a primary alcohol. And the primary alcohol that comes from here is going to be ethanol, not this diol. You see that? So that's why D is also off. Then question 30, when heated with potassium hydroxide dissolved in ethanol, halogenoalkanes, I actually said it before, can undergo an elimination reaction to form what? Alkenes. But if this one is dissolved in water, just aqueous, then we form alcohols under substitution reaction. You see that? All right. Then they are saying, what are the possible elimination products when 2-bromobutane is heated with potassium hydroxide dissolved in ethanol? It can be potassium hydroxide or sodium hydroxide. Okay. So we have 2-bromobutane. What is 2-bromobutane? I can put the bromine here, then the H here, then CH2, CH3. Now this one is going to give us two products from here. So this carbon holding the bromine is going to lose the bromine. Are we there? So we shall have CH there. Then this carbon here attached to this one that is holding the bromine is going to lose a hydrogen. So it is either this carbon that loses a hydrogen or this carbon here. So if this one loses the hydrogen, then we shall get the CH2, then the double bond here, and then CH2, CH3. This is but1-ene, okay? So we form that but1-ene. That is 1. Then 2, we can also have this other carbon losing the what? The hydrogen. So if this one loses one hydrogen, then we shall have CH3, then CH. Remember, there is a double bond created there. It's an elimination reaction. And then this is but2-ene. So they are saying, what are the possible elimination products? We have but1-ene and but2-ene. So this is but1-ene only. This is but2-ene only. So that is off. This is off. This is but2-ene, and then this is but1-ene. This is correct. That is what we have seen there. Okay. And then here they are saying it is producing a diene. No, it will produce this diene if there is also, let's say, another Br here, and there is one hydrogen here. So there will be a double bond created here or here, like that. You see? So we have only one bromine. So that is why we cannot form this other one here.